Welcome back, fellow mitochondriacs, to another episode of Cancer as a Mitochondrial Metabolic Disease. We have talked about tumor hypoxia or low oxygen levels and why it matters, metabolic reprogramming, chemotherapy, immunotherapy, and radiation therapy resistance, and as a marker of poor prognosis. But how does it actually happen? Why do tumors become so oxygen deprived? The real answer reveals some of the most fundamental problems in cancer biology. In this video, we'll break down the key mechanisms behind tumor hypoxia, including abnormal tumor vasculature, diffusion limitations, and metabolic demand, and how these factors interact to create low oxygen environments. So without further ado, let's get into it. So this is going to be an unexpected part 5 to the tumor oxygenation kind of mini series. And the reason I'm doing this video is because I got so many excellent and very valid questions about how does this actually happen? Is it my sleep apnea? Is it my this? Is it my that? Is that what's causing this? Or is it some other process? And I tried to answer as many people in the comments as I could, but I felt like this was a critical area of understanding that I wanted to hammer in to all of you. And so I am going to make a short video about how this actually happens. So the first paper I'm going to look at is titled Hypoxia and the Tumor Microenvironment that was published in 2021. And in the abstract, it says, hypoxia is an important feature of the tumor microenvironment and is closely associated with cell proliferation, angiogenesis or the creation of new blood vessels, metabolism, and tumor immune response. All of these factors can further promote tumor progression, increase tumor aggressiveness, enhance tumor metastatic potential, and lead to poor prognosis. These are things we talked about in the last videos. In this review, these effects of hypoxia on tumor biology will be discussed along with their significance for tumor detection and treatment. So I wanted to pull out the parts of this paper that were relevant to us looking at how this actually is set up. So in this part called hypoxia and proliferation, it says here that oxygen is required for efficient AT production, and hence hypoxia is unsurprisingly linked to reduced cell proliferation. In the classic Pasteur effect, while yeast growth is reduced under anaerobic conditions, their rate of sugar metabolism is increased. In tumors, as demonstrated by Waki et al., well-oxygenated cells, which are closely adjacent to functional blood vessels, have higher proliferation rate, while hypoxic cancer cells, generally located 100 to 200 micrometers away from functional blood vessels and or close to necrotic areas, have relatively low proliferation rate. And that's where the cancer stem cells or the cancer tumor initiating cells generally are seen and hang out. Several other studies have also revealed the mutually exclusive pattern between cell proliferation and hypoxia in both microscopic avascular and macroscopic vascularized tumors. Further, tumors that are hypovascular may appear dormant with cells either dividing very slowly or resting in G0, though it has been found that dormancy can result in high proliferation being offset by apoptosis, preventing growth beyond a certain size threshold. The next section is titled Hypoxia and Angiogenesis. Angiogenesis is the process through which new vessels are formed, mainly from existing vessels by means of sprouting. ECs lining the luminal surface of blood vessels are normally quiescent, but during development, wound healing, and disease, they can be activated to enter angiogenic process. Tumors initially form in a pre-vascular phase when the tumor diameter is less than 1 millimeter. There is no vessel formation, and the cells mainly depend on permeation to acquire nutrients. As the tumor grows, vessels develop and cells acquire nutrients through angiogenesis. If the angiogenesis fails, the lack of oxygen or other nutrients restricts the tumor size to 2 to 3 millimeters. Studies by Lee et al. Have shown that hypoxic status is closely associated with blood perfusion. In the peritoneal metastatic colorectal cancer animal model, they found that microscopic tumors less than 1 millimeter in diameter were avascular and extremely hypoxic, while those greater than 1 to 4 millimeters in diameter, vessels had developed and hypoxia was minimal. As tumor volume increased, the rapid expansion of tumor cells exceeded the local blood supply, and the inefficient tumor vascular system could not provide enough oxygen and other nutrients, resulting in hypoxia and macroscopic tumors. Angiogenesis is activated in response to hypoxia via the HIF-1 pathway, hypoxia-inducible factors that we've talked about over and over again on this channel. And the consequent production of vascular endothelial growth factors, VEGF, both tumor and stromal cells, tumor-activated ECs, have distinctive gene expression profiles and luminal cell surface receptors, resulting in abnormalities in tumor vasculature. This abnormal vascular network is characterized by leaky and compressed blood and lymphatic vessels, leads to further regional hypoxia, creating a vicious cycle. As a result, tumor cells move through periods of hypoxia reoxygenation that produce a more aggressive phenotype. So what is this paper effectively saying? It's saying that there are multiple reasons why these tumors are hypoxic. They either don't have any vasculature at all, which limits their size because they can't get nutrients and they're super hypoxic, or they have ineffective blood vessels that are highly compressible, they're leaky, they're malformed, and nutrients and oxygen can't get to those tumors, even if they're bigger, because of the poor vasculature or the vasculature that's not actually getting into the meat of the tumor. And then there's not enough distance between the cells that need nutrients and oxygen. That diffusion difference, or the distance between the vessel itself and the tumor tissue, is too far for it to diffuse over there. So they're limited by the ability to obtain nutrients that way. And then we're going to go to the next paper, which was titled Tumor Hypoxia from Basic Knowledge to Therapeutic Implications, that was published in January of 2023. And it says here, diminished oxygen availability termed hypoxia within solid tumors, one of the most common characteristics of cancer. Hypoxia shapes the landscapes of the tumor microenvironment, TME, into a pro-tumorigenic and pro-metastatic niche through arrays of pathological alterations such as abnormal vasculature, altered metabolism, immune suppressive phenotype, etc. In addition, emerging evidence suggests that the limited efficacy or development of resistance towards anti-tumor therapy may be largely due to the hypoxic TME. I would also say the acidic TME as well. This review will focus on summarizing the knowledge about the molecular machinery that mediates the hypoxic cellular responses and adaptations, as well as highlighting the effects and consequences of hypoxia, especially for angiogenesis regulation, cellular metabolism alteration, and immunosuppressive response within the TME. So we have already went through how the hypoxia component in the TME, or the tumor microenvironment, leads to therapy failure and leads to immune suppression. So we're not going to go into that part of the paper. What I want to look at this paper for is it gives us some further understanding about how the hypoxia is created within the tumors. And then there are some graphics that I'm going to show afterwards that help illustrate these points that have been made by the texts above. So I like this one because it answers the question that a lot of people have been having, right? How does hypoxia affect the TME? How does hypoxia actually get set up? The fast proliferating rate of tumor cells is often accompanied by poor vasculature formation or vessel formation, therefore leading to the development of intratumoral pathological hypoxia or low oxygen. Although HIF could stimulate the formation of new blood vessels in the tumor region to compensate for the shortage of oxygen, however, the tumor vasculature is featured with poor organization and irregular architecture, which is easy to collapse under the pressure of tumor formation and stromal growth. This phenomenon causes an irregular oxygen supply and an overall hypoxic environment in the tumor. So although the hypoxia and pseudohypoxic factors that stabilize HIF, and HIF has the power to make new blood vessels through activation of VEGF and other things, like it said in the previous paper, the vasculature that's made by VEGF under these HIF control is very poorly organized, and the irregular architecture and kind of leakiness of the vessels that are made, that are kind of like diseased vessels, lead it to be unsustainable to provide oxygen to these tumors. And so it leads to an overall hypoxic state within the tumors. The tumor microenvironment, TME, is the ecosystem that surrounds the tumor cells, which is comprised of non-cellular and cellular components. The non-cellular components include the extracellular matrix, ECM, various signaling molecules such as cytokines and chemokines, and the chemical milieu, including the pH, acidic pH, PO2, nitric oxide, and metabolites. The cellular components mainly consists of immune cells, stromal cells, and blood vessels. The TME is characterized by several notable features such as low extracellular pH, aka acidic pH caused by the lactate and succinate building up in the tumor microenvironment, high levels of reactive oxygen species or oxidative stress environment, hypoxia, and a general immunosuppressive niche in comparison with normal tissues. Basically, that pH differences, the low oxygen, the reactive oxygen species, the inflammation, etc., from the cytokines and chemokines leads the immune system to be effectively suppressed, which is what leads to immunotherapy suppression as well, or resistance. Crosstalk and mutual causal relationship may exist between each of these characteristics, while hypoxia could stand out as the prerequisite above all in the TME. I think it's debatable, but it's important. There's no question. So let's take a look at some pictures that see if they can help us understand what's happening here. So here is a blood vessel. And then what's going to happen is because the HIF signaling and VEGF signaling, they're going to try to sprout new blood vessels actually into the tumor. And then depending on the pH and the distance between the vessels that are somewhat healthy and or unhealthy and the cells, that distance is important. And then the level of diseased blood vessels is important. And then also the amount of extra cells that are supporting the tumor itself, like the stromal cells, immune cells, et cetera, which also are going to be eating up the oxygen. So what happens is the closer you are to a blood vessel, you see these are normoxic, quote unquote, cells. That's probably debatable, but less hypoxic. And then there's more hypoxic, and then there's like probably anoxic areas here. You can see here from normoxic to hypoxic, right? And this area here is a lot of times what is driving the other areas, and that is shown in the subsequent slides. And then this is also where a lot of times the necrotic core is at. And then a lot of times there's also the tumor initiating cells or cancer stem cells, the same names for the same things. And so this is the tumor architecture. And so again, there's going to be areas that are less hypoxic, and there's going to be areas that are more hypoxic, and there's going to be areas that are even in the deepest area of the tumor, which is probably anoxic or even low to zero oxygen whatsoever. So it's kind of heterogeneous in terms of the amount of oxygen that are in these tumors. And then I picked this one because it's kind of the same picture, but it's flipped on its side, right? So instead of the blood vessel being on the left side, it's on the bottom, right? And then the more normoxic cells versus hypoxic versus anoxic and necrotic cells are in the core of the tumor, right? And then what you see here is that this graphic is saying the deeper we go in here, normoxic versus hypoxic versus anoxic, then chemotherapy, radiation therapy, I would add immunotherapy resistance and metastasis risk, surgery failure, et cetera, increases, right? So the O2 gradient here, the oxygen is at the highest. Maybe this is close to a major blood vessel where there's plenty of oxygen that can get into those areas. This is similar to the tissue of origin, whereas as we get into the tumor, we're losing oxygen and we're much more hypoxic, 3 to 6 times more hypoxic than the normal cells. At the end of the spectrum, the most hypoxic, most poorly vascularized areas, these are basically anoxic. This could be 10 to 100 times less oxygen than a normal cell would have. So this is kind of showing how and why, right? And then because of the hypoxia, here's HIF1 alpha. This is kind of a neat graphic. So if there was hypox or normoxia, then generally hypoxia-inducible factors would get degraded, but because there's hypoxia, it gets stabilized, and then it has all the metabolic reprogramming and all the cancer promoting effects that happens. So it becomes like this self-fulfilling prophecy, or kind of like a vicious snowball at least. And then I picked this one because of this graphic right here. So this one's titled Hypoxia Signaling the Metastatic Cascade, and it's published in June of 2016. And it says hypoxia is a potent microenvironmental factor that promotes tumor metastasis. Recent studies have revealed mechanisms by which hypoxia and activation of hypoxia-inducible factors dependent signaling promote metastases through the regulation of metabolic reprogramming, the stem cell phenotype, invasion, angiogenesis, immune suppression, and pre-metastatic niche, intravasation or extravasation, and resistance to apoptosis. These discoveries suggest a novel paradigms in tumor metastases and identify new opportunities for therapeutic interventions in the prevention and treatment of metastatic disease. Here we review the impact of hypoxia and hypoxic signaling pathways in tumor and stromal cells on each step of the metastatic cascade. And you see here that the hypoxic core, or the anoxic core, where there's a lot of signaling from hypoxia-inducible factors, is what is being secreted in the local environment that leads to angiogenesis, cancer stem cell formation, metabolic reprogramming, invasion of other tissues, extravasation, resistance to apoptosis, and immune suppression. And it leads to ultimately metastatic spread. So hypoxia, as hopefully I've outlined somewhat well in the last now 5 videos, on hypoxia is a huge problem and a huge lever for us to be potentially able to pull, which is going to set us up nicely as we talk about oxidative therapies. And in the next videos, I'm going to be specifically talking about the employment of potentially normobaric and hyperbaric oxygen as a way to address this problem and add additional oxidative stress as kind of the final hammer for ketogenic metabolic therapy. If you like videos like this, please like, share, and subscribe. And until next time.